I'm going to talk about some research that we were doing. So the main question that we asked is if gas is important or could be important for planet migration. And I will summarize what our findings here. Sorry, the control is too fast. Green. Okay, thank you. Okay. So the important point is that we know that dust is everywhere in the universe, it's in the galaxies, it's in the protoplanetary disk, so we observe dust everywhere. And it is typically accepted that the gas-to-mass ratio in a protoplanetary disk follows the same ratio as in the interstellar medium, and we assume it to be the 1%. We don't have strong observational evidence pointing this value today in protoplanetary disk, but this is just an assumption that I'm going to make during the talk. So the important question is that relevant for planet migration? And to understand that, we first need to understand what planet migration is. Planet migration has the classical planet migration has two important sources of torques. And one is what is the so-called Lindblad torque, and the other one is called orbital torques. These two torques usually in standard disks have a different sign. So the Lindblad torque is usually negative and is produced by the spiral wake. We have an inner spiral wake and an outer spiral wake. The inner spiral wake is ahead of the planet, so exerts the positive torque. The outer spiral wake makes the opposite, of course, and the net balance of these two spiral wakes is a net torque that is usually negative. It's a small quantity. These two independent torques are strong, but the balance between these two wakes is usually a small quantity. And on the other side, we have the orbital torque, and it's the torque produced by the horseshoe orbit. So we have a particle here orbiting around the planet. This is a frame of reference which is fixed with the planet. In blue here, we have the star here in yellow, and the particles move in the horseshoes. These are a special set of orbits in the restricted three-body problem. And when the particles jumps from an outer orbit to an inner one, loses angular momentum. And then it approaches again to the planet, and in the other side of the orbit, it jumps from an inner orbit to an outer orbit and gains angular momentum. In a typical scenario in a protoplanetary disk, the horseshoe orbits are asymmetric for the gas components, so the net torque is usually something. It's not something that averages to zero. And this is a positive quantity. This is not strongly dependent on this physics. So I mean, for realistic disk, it's usually very well known, and we only have small corrections if we change the disk properties. And on the other side, the orbital torque depends strongly on the gradients of the quantities. Depends very strongly on the gradient of density within the horseshoes. And because everything affects the gradient of density, also depends on temperature, and at the end, Bohr density and enthalpy. I believe that the proper characterization of orbital torques is crucial to describe the migration history of planets. So why is this important? Because if we want to find some contribution from dust here, we know that dust is, the mass of dust is very small. So we shouldn't look here because we know that gas torque dominates in the large case, but we should look at the orbital region where the mass is very close to the planet and the gravitational effect of dust can be stronger. So there is a very simple picture to understand where we should see to find orbital torques. We know that the dust particles are subject to a radial drift because of the torque exerted by the disk. This is the headwind because the gas torque is sub-Keplerian, and the dust torque tends to move at the Keplerian speed, so we have a headwind acting onto the dust particles. In one case, we can imagine a dust particle here. We have a planet in the orbital frame, and we have a particle that is drifting very fast here. And it approaches to the planet very quickly and doesn't react very much by the torque exerted by the gravitational force exerted by the planet. And this is a regime where the headwind torque is larger than the planet torque. So we don't expect significant modification, and we expect to have similar densities in front of the planet and behind of the planet because we have a continuous flow of dust in that region. On the other hand, we can also consider the case where we have particle sizes that are able to drift at a speed much smaller than the orbital time speed in this frame of reference. This is a region of the parameter space where the planet torque is much larger than larger or order of the headwind torque. So in this case, we can have particles drifting here. They are approaches to the planet, and because the planet tries to push away all the particles that approach to it, then the particles move to here, and because the domain is periodic, this is azimuth in the horizontal axis. The particles approach again on the other side, and then the particle cannot cross the horseshoe. This is a region of the parameter space where we should expect the formation of a gap in the horseshoes. And this is called, for example, for the gas case, we can imagine the drift as the viscosity and the planets as this is the gravitational force of the planet, and the balance between this torque, the headwind, which is the viscous torque in the gas disk, is compensated by the planet torque, and we have the formation of the gap. But we have a very interesting case where when the planet torque is order of the headwind torque. In this case, the interplay between the radial drift of particles and the torque exerted by the planet can create a very asymmetric region in the horseshoe. And this was recognized in the past, and people have called it type 3 regime or runaway migration regime. And it's a region where we can create some sort of partial gap and accumulation of mass depending on the drift speed of the planet, and can create a strong torque because there is a strong asymmetry of mass very close to the planet. Okay, so if we do one experiment, one simulation, we have here a planet in a gaseous disk, and we have a dusty disk here. I have chosen the parameters in this simulation just to enhance the effect I want to show. We have particles drifting here in a frame of reference that is rotating with the planet located here. It's here in the gas component. This is the y direction, x direction, and the star is located at the center. The particles drift here. They jump because of the torque exerted by the planet. In this case, the headwind is order of the planet torque. And then because we're in the co-rotating frame, the particles approach again to here, feels a perturbation because of the planet, and they continue drifting, and they spiral inwards in the disk. So we see that a very deep underdense region develops in one side of the planet. So this creates a strong asymmetry and is able to exert torque. So the question is, the torque of this kind of hole is important or not? Can produce a significant effect for planet migration? So in order to understand that, I want to share with you some, for me, very simple calculation. It's a very interesting case where we can just do or almost solve the problem in 30 minutes with pen and paper. So let's see if I can convince you about these arguments. This is interesting. It's very interesting. Based on the plot I showed you before, it's interesting to ask how big of torque can an asymmetric orbital region exert onto a planet. So let's assume a very simple model where we have a planet here, and we have a horseshoe region characterized by some width, this xs, and one delta parameter that tells us how depleted is the horseshoe region. It's a very simple model. We have two step functions, one step function for delta and one step function for radius to model the horseshoes. So now the question is, how can we calculate the torque here? We have, this is the torque definition. I'm interested in the z component of the torque. I'm just doing the calculation in 2D, so this 3 should be 2, sorry for the mistake. And this is the tangential force exerted by the planet, multiplied by the density, and this is the total torque. This is just a normalization factor, and we can now compute this integral, assuming the density distribution of the previous model, and we can solve the equations. And now we can ask, once we have solved this integral, what's the maximum torque that an asymmetric horseshoe region can exert? And this is very easy. So from symmetric reasons, it's easy to believe that the maximum torque will be exerted when half of the horseshoe is depleted. I did that, so we can take the derivative with respect to this parameter delta of this equation, evaluate it to 0, and find the maximum. And we find this expression, very simple expression. This is an estimation. And so what is important is the torque exerted by this horseshoe region that I call it dust is proportional to the size of the horseshoe. This makes sense because a wider horseshoe region has more mass, so it's able to exert a stronger torque, and it's inversely proportional to the smoothing length that I'm using to compute the torque. And this is obvious because if I do a horseshoe region that approaches for example, to the inside of the planet, the gravitational force will diverge, of course. But we have good arguments just to estimate this smoothing length that is given by the third dimension of the disk. Okay, so the next question is, how can we estimate the size of the horseshoes for the dust component? And it's very interesting to realize that we can answer that question from previous results obtained for the gaseous component. The width of the horseshoe region, we know that scales not only with the mass of the planet, but with the temperature of the disk, actually with the scale height of the disk. And this is easy to understand. Why is this the case? Because in the momentum equation for the gas, we have the pressure gradient, and we also have the gravitational term, the gravity gradient. The combination between, in the case, let's imagine for one moment that we have a very massive disk, a very massive planet, sorry, that where the pressure, the gravitational force dominates over the pressure terms. In that case, in that case, the mass of the planet, there's some water? No. Okay. In the case of where the gravitational force dominates, we expect the size of the horseshoe region to scale with the Roche-Lobe of the planet, as is a very well-known result from the three-body problem. But when the pressure term is important, so the pressure is what is linked to the temperature of the disk, the size of the horseshoe region should scale with this pressure term. So we know for small mass planets where the gravity term is not important, is not so strong as to neglect the pressure term, the horseshoe should scale with Q over H. This is the plot, the result from Parde-Cooper and Papelesso 2009, and this is the scaling law for low mass planets. In the horizontal axis, we have mass. And in the case where we have very massive planets where they start to compete against the pressure term, we have another slope that scales with the Roche, the Hill sphere of the planet, and this is identical to the restricted three-body problem. So based on this, so what's the connection between these results and dust components? And it's very simple to understand that. This is the momentum equation for the gas. This is the drag force term. This is proportional to the relative velocity between the gas and the dust. We have the pressure, the gravitational potential of the star, and the gravitational potential of the planet. So in the regime of very small dust particles, where they are very well coupled to the disk, we expect the dust to be highly affected by pressure gradients. So for very small dust particles, we expect to have a size of horseshoes that are proportional to the horseshoe of the gas component. And this is actually the case. Very small particles has a horseshoe region that is much smaller than large particles. But this is not. This is only because of the coupling to the gas. It's not because dust particles don't tend to have a horseshoe that scales with the Hill sphere. So what is important is for a fixed planet mass, the size of the horseshoe scales depends strongly on the size of the particle that we consider. Okay. Now we have an equation that tells us the maximum torque that an asymmetric horseshoe region can exert, and we also know that we have two regimes where the size of the horseshoe is different. So now we can build curves where we plot the maximum torque as a function of the mass of the planet. And here in the green curve represents the migration rate, the torque exerted by what is called type 1 migration, so the standard result for migration in gaseous disks. And I overplot here two curves of the maximum torque that can be exerted for an asymmetric horseshoe region of dust, assuming 1% of dust. Depending on the size of the horseshoe, this is gravitational. The red curves corresponds to the case where the horseshoe scale with the Hill sphere of the planet. Obviously it's larger. But what is important here is that for very small mass planets, we can obtain dust torques that are very, very strong compared to the gaseous case. So if we want to find an important effect for planet migration due to the dust component, we have to look at small mass planets. If I change the mass of the dust, I only shift the red and black curves vertically. So the place where the green curves intersect the black and the red ones is the cutoff where we expect the dust torques to vanish, because we don't have enough mass to modify the force exerted by the gas component. Okay, this is one important result. But now the question is, how can we modify the horseshoes? How can we obtain asymmetric horseshoe regions? And the answer for that is we have to compare the horseshoe libration time and the drift time scale of dust. So if, as I said at the beginning, if dust drifts very fast, we will not obtain very asymmetric horseshoes. And on the other side, if the dust drifts too slow, the planet torque will be important and we create a gap. So now we have to find the region in the parameter space where the drift time scale is order of the horseshoe or smaller than the horseshoe libration time to create these asymmetries. So we did that, and this is what you obtain. So now these are isocontours of horseshoe libration times divided by drift time scale as a function of the Stokes number of the size of the particles and the mass of the planet. And we see that there is a region in the parameter space which is above of the black curve where the dust cannot cross the horseshoes. So we expect above this black curve to see a gap formation in dust component. In the very inner regions here, we have is the place where the drift speed is much faster than the headwind torque is much larger than the planet torque. So we don't expect to have a strong modification to the horseshoes neither. Okay, so that was the motivation, and it's almost says where we should look in the parameter space, where we should perform all the simulation if we want to measure the contribution of this new effect. And we did that. So now this is an exploration by varying the particle size for a fixed mass planet, and we can see all the regimes playing different roles. So very small particles tends to follow the gas mostly. The horseshoe region is smaller that compare to the case where the Stokes number increases. So now the question is how large is the torque in each of these cases? So we did now the full systematic exploration of the new effect. This is a set of 200 simulations, very high resolution simulations, where we have changed the mass of the planet and the Stokes number according to the previous calculation I showed you. The colors are, is not very easy to read this plot. This is in logarithmic scale, is the dust torque compared to the gas torque. So values equal to 1 are dust torques equal to gas torques in this plot, to 0, sorry. So white colors here means most of the plot is, don't look at this region. Most of the plot corresponds to positive dust torques. And because I'm dividing here by the absolute value of the gas torque, in this case, white colors means zero migration. These are places where dust torque balance the gas torques identically. Blue regions here are to the right are dust torques that are much stronger than gas torque in these simulations. And red colors are still positive dust torques, but they are not enough to counteract the effect of the gas torques.
Sorry, is the gas torque just the
type 1 migration? No, it's a full torque. It's Lindblad plus co-rotations, yes. So what is important here is that we observe the same shape of, so if I plot isocontours of torque here, we can observe the same shape that I derived using the simple calculations before. And we can also see that for large particles, these are quite large particles, are planetesimal, okay, well, that depends, or large pebbles, that depends on the density of the gas. We can see that dust is able to exert a huge torque. So it can be 10 times larger than the gas torque. All this mass was built assuming only 1% of dust in the simulation. Actually, in a real scenario, what we have to do is to convolve this map by a particle size distribution stored in the disk. But all the results are here. And the numbers to the right are just the gas torques that are useful to compare if you want to do your own simulation. And, or, for example, if you want to derive the absolute dust torque from this plot to include this effect in planet population synthesis model, for example. The region here is a region it's a very interesting region where some sort of chaotic behavior occurs. This the places where I have crosses here corresponds to dust torques that are negative. So in this region, the dust torque makes the opposite effect, so the planet drifts much faster than the gas torque in the gaseous case. And this was a region where it was very difficult to find convergency for the results. And this is because there is a transition where the headwind torque is very strong compared to the planet torque. So particles approaches very, very close to the planet in this region. So it's challenging numerically. That's why it's a special region for our parameter exploration. So, and this is just work in progress. Now the question is, how important is feedback for all these results? For feedback, dust feedback was not included, and that was reasonable because the total dust is the total mass content in dust is small. It's just 1%. But still, we wanted to check if everything makes sense in a more general case. So we have assumed a particle size distribution characterized by the minimum size and maximum size particle, and we have a negative slope, and we characterize our distribution by several bins. And this is how the results looks like. We have the gas component here, and these are different dust species. So we have we can observe a continuous transition between the different from one regime. This is a very well-coupled regime to the regime where this kind of hole develops and creates a very strong torque. If the total torque in this case is dominated by dust or not depends on the slope of the dust distribution that we're using to characterize the distribution. In this case, most of the mass is stored in the largest particles because it's a power law. It's more or less a steep slope. Was a slope minus 3, so minus 3.5, so was the classical one. But the maximum Stokes number was quite large. And this is the result. This is the gas torque, the blue curve. And we can, these are all the other torques. The colors are in the legend of the plot. And the black curve is the total torque in the simulation. So it's the total, the total torque, the sum of the gas torque plus the dust torques. So we can see that in this case, we can obtain outward migration with just 1% of dust. Of course, I insist the result of obtaining outward or inward migration will depend on the dust distribution that you assume. So here I am assuming that most of the dust is stored in the most efficient case for this mechanism. We can also increase the mass of the planet, so do the same exercise with different planet mass. So this is almost in the limit where the headwind torque is smaller than the planet torque, and we can see here that for some particle sizes we start to form a gap. And when we form the gap, since most of the mass is in these particles, there will be a deviation from all the calculations I showed you, and there will be important or unpredictable results from the total torque felt by the planet. And in this case, in the beginning, this is the dust torque of the largest particles. In the beginning, when this kind of holes start to develop, we obtain strong positive torques. But when the gaps start to form, we shut down the flux of pebbles in this simulation, and then the total torque decreases, and we recover again the gas torques. However, the pebbles cannot accumulate forever in the outer region of the planet. So at some point, the edge of this gap could become unstable, and we should have a massive flow of pebbles inwards that can also modify migration. These are just two examples, so this is work in progress, and it's very preliminary. So my final comments here. I think, or I hope, I convince you that large torques can arise from the dust component. We don't even need to assume small dust to gas mass ratio in order to get that kind of large torques. I didn't say that, but I want to comment this here, that dust torques, I said you that dust torque can be up to 10 times larger than gas torques. So dust torques can be larger than thermal torques, these kind of torques that arise from the heat emitted by the planet. So we have here potential to change the migration rate of the planet dramatically, and this has also the potential to become the dominant effect in some parts of the formation history of the planets. So what is important to emphasize here is that there are several caveats in these results, but I think it's the first step to start to study dust torques. It's important to understand that a realistic assessment of dust torques requires, of course, realistic models for dust size distribution in protoplanetary disks. We need to understand very well how dust evolves close to the planet. But my final comment here is it can be that this effect, it can be that in a real protoplanetary disk that I don't know how this, I think we don't know yet how protoplanetary disk is. We don't know the dust distribution, but we know something that we know very well is that planet migration is due to a subtle balance between gravitational forces, for example, in the gas component exerted by the spiral wakes or exerted by the orbits of in the horseshoe region. Because of this, even if the dust mass is small, if we have strong asymmetries of, not necessarily strong, but asymmetries, subtle asymmetries, but close to the planet, we can still exert a strong force onto the planet. So the question that I think we should try to answer is how important or how strong needs all these asymmetries to be if we want to modify the migration history of the planet. Yes, that's all of my talk. Thank you very much for your attention.
Questions, lots of questions. Okay.
You presented a very nice argument of how the width of your horseshoe scales. I'm curious, and you said the other thing that determines the strength of the torque is the distance of closest approach, essentially, to the planet.
Yes.
Is there a similar nice argument you can make for understanding that distance and how that changes?
Actually, the distance that you assume if you have very small particles is the vertical extent of the disk. So this distance should scale with h. For small particles, at the end, I think it's not very important, that distance. So the question is, how many particles approaches actually so close to the planet? If you have the regimes where the hole develops, we know that most of the torque is produced because of the vacuum of mass, of the depletion of mass in one side of the orbit. And in this case, the approaching particles are not so important to set the final torque. I think this question is important if one needs to assume that particles are or not accreted in that region. Because, for example, if particles approach to the planet and they tend to jump, and we don't know how close these particles approach to the planet, this could have consequences for the topology that arises from the interaction with the planet. But shortly, the answer is, for dust, I don't have a simple argument to say you what's the closest place where a particle approaches. No.
So you mentioned that asymmetries in the horseshoe orbit can lead to positive corrotation torques. And maybe one possibility as well, that I guess is the one you're referring here, is thermal torques, this accretion of planetesimal.
Yes.
How do you compare these two processes now, dust and
Yes. Here, I'm assuming here that approaching particles to very, very close to the planet are not important in setting the final magnitude of the dust torque. So in this scenario, I can still assume that particles that approaches very close to the planet are fully accreted by the planet. And in this case, I have the heat released by the planet. So these two effects, I would say, they can survive together. What is important is that this accretion also modifies the dust distribution close to the planet, and the dust distribution also modifies the opacities. So we have now a double effect where the dust torque also modifies the opacity and can have implication on the heating on the thermal torques.
Jeremy, and then Simeon.
Questions about the Lindblad resonances.
Yes.
So I happen to have been thinking about this in connection with dust recently. So if you go back to the original paper by Goldreich and Tremaine,
Yes.
you see in the case of a symmetric, equal and opposite torques on the two sides.
Yes.
The contribution from Lindblad resonances closer and closer to the planet diverges until one hits something called the torque cutoff.
Yes.
Which can be simply understood as which is roughly at the disk thickness.
Yes.
Away from
of course.
the planet. And it can be understood by saying that a steadily moving body can't excite a wake unless it's moving faster than the sound speed. So only the gas which is far enough away to be moving supersonically.
Yes.
All right. Now consider dust. It has only 1% of the mass density, but it has a much smaller effective sound speed. And the combination that matters is sigma over sound speed squared, it turns out. So I would have thought there would be a large Lindblad contribution, at least in the quasi-linear regime where the planet has an infinitesimal mass and we don't have to worry about its Hill radius, from the dust that comes very close to the planet. But you have somehow the Lindblad resonance, and it would be an asymmetric contribution because of the headwind. Dust is drifting. You seem to have dismissed the Lindblad torques immediately, and I didn't quite understand where they went.
Okay, no. Yeah, no. I didn't miss any torque here in my calculations. It was just in my explanation. And of course, all the Lindblad torque is present here in the simulation, so I didn't do anything. So the result of this planet torque is the Lindblad torque is the
Lindblad torque due to the dust, I should be clear. This is
Of
the
course.
dust contribution to the Lindblad torque. It's in there, you say.
Yes. Yeah, so I mean, I'm computing the force due to the mass distribution there. So I'm not separating co-orbital or Lindblad torques in my results. That was just for the explanation. But the dust torque is a combination of very complex effects playing around at the same time. So it's a combination of course of the Lindblad resonances modifying the gas distribution. This changes the pressure distribution close to the planet, and there is also this effect that you are pointing about the.
What confuses me is that your net torque from the dust is almost always positive. The gas, it's usually the other way.
But you have the headwind is removing the angular momentum.
Okay, we'll just finish with Simeon.
Didn't quite understand the importance of the headwind torque that you mentioned way at the beginning. So there were regimes in which this effect could play a role. So am I correct in saying that you predict that none of this should matter if the disk has no global pressure gradient? There's no headwind torque, then none of this happens.
Exactly.
So then it's very different from type
Yes.
3, right? Because if you then start to move the planet, you start to create a flow past the planet of dust particles because the planet's moving with respect to the dust. But then none of this doesn't.
No, I would say it's the same, because what is important at the end is the relative motion between the dust and the planet.
But then it's not the headwind torque that matters, because in that case the headwind torque is 0. What's the quantity that determines then whether this is important or not?
The quantity that says if this is important or not is if the particles are able to cross or not the horseshoe in a time faster than the liberation time scale. And does not depend on the headwind per se, it depends on the relative flow of particles in the horseshoe. So the headwind is just a mechanism to produce naturally this flow. So it's a carrier of the angular momentum.
Yeah, so it can be you can turn it around and say, well, if it's either, so it's the planet migration speed can take that role as well, or not?
Oh. That depends on how strong is this torque. But I expect, for example, if the planet start to migrate outwards, so let's say that we have the headwind, the planet start to migrate outwards, and you have now a relative velocity that is enhanced, so the dust flow will be faster now in this new regime because the planet start to migrate outward, and this will start also to change the regime where we have the most efficient dust torque. So this kind of hole will start to close because of the higher speed of the planet with respect to the dust, and then we should have some sort of steady state. So I don't expect this is some kind of a runaway process. But
Okay, I think we should stop now, break for coffee, and thank all the speakers again.